So I would like to introduce the Dynamo script for calculating adaptive kitchen modules and the Revit model that works with it. A few words about the model itself. This is a simplified model of the modular kitchen that was developed as a part of the Soul Kitchen project. My idea was that it's interior partition wall that works as a kitchen, and it could be adapted to any height, any width of the room, and could be dismounted and installed in another room if it's necessary. So how it works? We have a Revit model with different elements like shelf nodes, structural frames. Each of these elements have different width, different amount of shelves, and potentially different height. What we can do, we can go to Dynamo script, go to this input parameter section, and for instance, we want to change it. We have a global height parameter, which basically is the height of the room. And it's a distance between these two elements. It's a floor and a ceiling. Now we have 2400 millimeters height from floor to the ceiling. And for instance, we want to, for example, we want to make it like 2700. We change it to that number and just press run. And model reacts to it. It adapts the height of every element, including the frame and shelves. Everything adapts to that distance. What else do we have? We have different inputs, for instance, global feet, which is a funny parameter. It's a distance between floor and the first shelf. So in case you want to have like some sort of a gap between the floor and the first shelf. It's also a global parameter, so it would affect all the elements 1, 2, 3. For example, now it's 135 millimeters. For example, want to have less, like maybe 80, 85. And or maybe even less, just to make it more obvious. As you can see, everything became smaller distance between floor and the first shelf. Also, we have global width. It works a similar way like global height, but it's a distance between wall to wall, this wall and this one, so it's the global one. If we change the width, for example, make it less, like 400, and as you can see, the way it works, it changes the last shelf. But if we calculate the distance of all the elements, it would be 4 meters, 400 millimeters. Why I made it that way, not another, is I wanted to have possibility to change individually these elements, the width of these elements, and when we have like global width and the width of every parameter, we need some sort of a gap closer, which this shelf works as like a gap closer. Global material thickness, as it says, it changes basically the thickness of all the elements which is supposed to be like wood, and as I plan to make it from the plywood, so it varies from 16 to 32. It's like a standard thickness of the plywood. So for example, if we change it to maximum 32, you can see how everything became much thicker. Go back and everything goes back again. So the next one is the first shelf width. So for example, if we change it, it became smaller. Another one, second shelf width. As you can see, the last one, the last shelf element is changing also. As I said, it's a gap closer, so the global width remained the same as it says in here. And the last one is the most, I would say, interesting one. It's an attractor point position, which creates this blue dot, and depending of the distance to this dot of every big shelf, it creates the different amount of shelves. So the closer the distance, the less amount of shelf it creates. So it's easier to show than to explain. For example, we have now the position according to x-axis and z-axis. If we change the position, for example, to that, you can see how very different it became. So the closer the distance, the less amount of shelves it creates. But this is not the only way to do it. We also could change the amount of shelf individually. But to do that, we need to prepare the script a bit. So now we can input the shelf amount for every shelf. So as it says, it's the same first, second entresol. I call that one entresol, and the third shelf is this one. So if we change this parameter to, let's say, 6 shelf for the first one, it individually changes it to 6. It's also changed the all other, but it's just because I just changed the inputs. Now it works separately. 4, go to entresol, which is this one. For example, we want to have 6, which is a very small amount between them. And the last one we would have like 3, for instance. The script also gives us information about the distance between shelves for every shelf node. So for the first one, now it's 441 millimeters. So for example, if we change the shelf amount, it also changes. So it's a very precise information. Also for the second one, the entresol, and for the fourth shelf. So how I created this script? I started with the Revit model, which is not that complicated. It's only 2 families. These 4 shelves is one family, and these barely visible frames is the second family. The shelf family is very simple, just basic, without any parameters family. If we go inside, we can see how it looks. And as you can see, there is a lot of different parameters, which are instance parameters. And these instance parameters allows us to manipulate the shelf differently depending on what inputs we make in the Dynamo. So for example, if we open the dialog with all the instance parameters and change one of those, we can see how it reacts. So if we change it to something crazy, not that crazy, yeah, it basically works according to these axes or depending on the position to other elements. And the second family is the frame. If we go inside, we can see that it's even simpler than the first one. And basically the only parameter, instance parameter that we need is this one, rel move height. What it does, it changes the height of the frame. Because the rest is basically static and it works as in real life, that the only thing that changes, that we can change in this frame family, is the height. So for example, if we change the height, it also works like in real life, like it's supposed to. It's not stretched, it just moves this frame element to adapt to the ceiling height. Yeah, and the rest is nothing special about it. So if we open the properties, we can see that it's very basic, generic floor, ceiling, and just very generic walls. We don't even need to have an instance parameter for it. And now the interesting part, which is the Dynamo script. So few words about the structure of the Dynamo script. So on the left side, which is in here, you can see all the inputs of the script. So for average user who probably gonna use this script, is no need to look at this messy right side, just to make changes in this smaller portion of the script. Okay, I separated the functions by color, and blue one is just for the frames, these ones, the barely visible ones. The green ones is just for the place and height of the side walls and also for the ceiling. These big ones are for the shelf nodes, which are the most changeable elements. So this one is the first. Second shelf is the pink one, and it's in here. Island is just downloadable element from the internet, and it's not changed at all, it's just about the position of it. Entresol in here, and the fourth shelf is in here. This gray one is all about this attractor point, which I explained it before. I've started making this Dynamo script by placing this family 4 times, just copy and paste, and selected each of those elements using this select model element node. This one for the first one, second one, here is the third one, and the last one. First thing we need to do is to place it not randomly, but on the same line on specific points. So we can see how I made it. Element set location is the node for it, and since we need a coordinate system, I thought that since all the elements are on the same line, we don't really need z-axis or y-axis. All we need is an x-axis, and the place point for every of this element is in the middle. So all we need is to take the width parameter and divide it by 2. So now the point is in the middle. So now we have the point which is 0 on Y, 0 on Z, and 400 on X. This is how it's placed. So the logic for the second one is the same, but since it needs to be a bit further, what we do here is the coordinate points. The nodes are the same: set, element, location, point by coordinate, but coordinate, as you can see, a bit more complicated looking. So what's different about it is we have A and B. So what A is actually the distance of the first one, the width of the first one, and B is the width. B divided by 2 is the distance of the second one, the width of the second one. And also we have 55, which is 55 millimeters, and it is the width of this frame which separates it. And when we calculate everything, the value became the value for the place point for the second shelf. And the logic repeats the same, but now we have not 55 but 110 seats, since the shelves already have 2 frames in here, and for the last one it's 3 times of 55. So when we have placed the elements on the proper position, now we can manipulate the parameters itself. Element set parameter by name is the node for it, and it has 3 inputs: element itself, parameter name, which should be exact name, and the value. So I combined parameter name and values into lists in order to just save the space. And here we have 2 items in it: the array number, which refers to shelf amount, so this is the amount of shelf, and between shelf. Between shelf is a distance between each shelf inside this shelf node, shelf block, and it's in here. And there is the same logic for every shelf element. It's the same amount of nodes and the logic behind it. So here I preserved the space for the global parameters. It used the same set parameter by name node and list, which consists all the shelf elements, and it uses, for example, material thickness, which is a global parameter. And as you can see, since we have all the elements collected and name, but the value is the same for all of those. So if we click and follow this line, we can see that the global material thickness affects all the elements of the shelf. Speaking of frames, since I made it based on the furniture family, it actually glued to this shelf, so it's very easy to place it just using the set location and point by coordinate. And as you can see, I didn't even need to specify the place, because the 0 for each of those frames is the shelf I placed it on. The only actual parameter which could be changed for those frames is height, and for those frames it's a global parameter, and actually it goes from the global height of the ceiling. But as you can see, the formula consists of -1 meter. Why so? Because as I showed before, the way how the height of these frames changes is a very specific way when we need to subtract the height of this frame itself. In order to create this wall, I used a bit different method than before. I didn't create it inside Revit. I used the Dynamo node for it, and in order to create it, you need to specify the start and end level for the wall. It's basically its height, type of the wall, and specify the points for drawing a line which it stands on. Since the y-axis is static, we just need to input the values, and since x-axis is dynamic, it changes all the time, then we need to use this kind of formula. And the last group of nodes, it's an attractor point nodes, and in order to show it better, I think we need to return the individual input to the attractor point input. So how to make an attractor point work? So first of all, we need to create this attractor point, which is just a regular point by coordinate. And what it has x and z value, like I showed at the very beginning. So here's the input values. And also, to make it more visible, I just created a regular circle around it. Actually, it's not a circle, it's a sphere, but in Revit it shows it as a circle. The second step is to calculate the distance between the points and the elements, which is these shelves. Basically, we take a coordinate for every shelf element and calculate distance using geometry distance to node. Now when we have a distance between the point and each shelf, we can make a trick using this remap range node and replace these numbers to a new ones, specifying the minimum and the maximum. And what this node does, it preserves the ratio between those numbers. Now when we have replaced numbers, what we need to do is to make it an integer, which means removing all those after the point numbers. And after that, it's the last step, we can just use it as an input for the array number, which is the amount of shelf for every shelf element in the project. I think the strong side of this project is that the group of nodes I used could be splitted and used in another project for different purposes and tasks. Thank you for watching.